In this presentation, we can discuss about structures and pointers. Structure is nothing but a contiguous chunk of memory like array. Name of the structure variable points to the beginning of the chunk of memory allocated for the structure variable. Indexing is a bit more complicated as different members have different size. That's the difference between array and structure. Also, in the case of structure, to correct the alignment, compiler adds some extra bytes called padding, which is not there in the case of array. So let's look at a program of structure in Visual Studio and see how the memory is allocated. Here we have a program which has a structure data type. It contains 4 integers a, b, c and d, all integers. So we are accessing and assigning some value to a variable of type myStruct, which we have seen here. So this is a very simple and straightforward program which includes structures in C. So now what we can do is we can look at the memory. So I have executed the program and the breakpoint has reached here. Now let's have a look at the memory of this particular variable. So in the memory, I'm going to type ampersand ms. 64 is allocated on the first 4 byte, which is nothing but 100 in hex. C8 is 200. 12C is 300 and 32 is 50. What this shows is it is a contiguous chunk of memory like array, and when we access each element, we are accessing offset from the beginning address. If you look into the rest of the program, we can see that an integer pointer is assigned this particular address, and we are using normal pointer arithmetic to access each element. So this is a, b, c and d. So the output of this program is expected to be 100, 200, 350. So this can be further proved by looking at the disassembly. So this is the disassembly of this particular code. So this is where the 100 is getting allocated. EBP minus 10H is the starting address. The total size of the structure is 16 bytes, and we have one more pointer variable here, so total 20 bytes. So that is what happening here. So ESP minus 14H. Now EBP minus 10H is the start address of the structure variable. We are assigning 100 to it. Next 200, 350. So it's all contiguous 4 bytes if you look at. Now again in this printf statement, proving the same thing. So the size of the structure variable is the sum of the size of its members. So in this case we have 4 integers. So 4 into 4, 16 bytes memory required for this particular variable. Now let's go back to our slides. So we have seen this case, all integers. There's a little bit of complication coming up when we deal with structures which has different types of members. So to understand structure padding, first we have to understand what is memory alignment. Memory alignment is a restriction from the CPU which should be respected by the compiler or whoever writes the assembly language. Due to performance reasons, most of the commercially available CPU mandates the access to memory to be X byte aligned when we read or write an integer value. Normally X is 4 byte in a 32-bit operating system, It depends on the width of single chunk of data CPU can deal with at a time. For example, in the case of double, it is 8 byte. The alignment restriction is 8 byte. So a double address should be 8 byte aligned, because the coprocessor deal with 64-bit data, not 32-bit data at a time. Root cause of the problem or the alignment issue is the size of single chunk of data CPU can handle at a time internally. In this case it's 4 bytes, is different than the smallest chunk of addressable memory. In our case we can address each byte, so each byte is addressable, or each byte of memory has an address, but the CPU handles everything in 32-bit. That's where the problem comes from. Compiler can force the CPU not to follow the alignment, or compiler can give CPU instructions which are not aligned, but it is at the cost of performance. With the help of this figure, let's try to understand the problem of memory alignment. So these blocks we see are memory addresses, so 0, 1, 2, 3, etc. By the design of the CPU can address or handle data which is 4 byte long. So each location is a byte in this, each block is a byte. So CPU can handle this much data in a stretch, provided that CPU is given address to this particular location. But if we are giving this address, for example, to access 4 byte, CPU has to do a read of this chunk and this chunk. From this chunk it will take this many bytes, and from this chunk it will take this 4. So 1, 2, 3, 4. So in this operation CPU is doing 2 read operation or write operation, whatever the case may be. But if the address is aligned, CPU can do a single read like this and get the 4 bytes in a single shot. You may ask the question, why CPU can't read this byte, this byte, this byte, and this byte in a single shot? The answer is by design of the CPU. That is how the CPUs has been implemented. All these addresses here are 4 byte aligned. CPU is okay with this kind of addresses. This is not, and this is not, and this is not. Now what is the problem if we don't give aligned addresses, misaligned addresses? So as we discussed, integer access will take up to 2 reads, which is almost double the work. It may take twice the amount of time. So it's all about performance. In olden days, CPUs used to give problems. Some kernels like Unix used to terminate the applications in olden days, but nowadays CPU handles it. So it's all about performance. In Intel x86 CPU we have byte PTR address, by which we can do a single read or write to a byte. Even if we are giving a dword PTR which has an unaligned address, CPU will read correctly. It is just the performance we're gonna pay. Normally compilers do not create this kind of instructions, so it will try to add some kind of padding to avoid this scenario. But compilers do generate byte PTR unaligned address, which is okay because anyway we are reading a single byte. So now let's discuss about structure padding. Structure padding is the additional memory bytes compiler adds to the structure variable to correct the alignment of its members. This is not specific to structures, but it is applicable for any kind of memory access. For example, local variables. But it is more visible in the case of structures because size of operator will give you a different value than the one you were expecting by adding the sum of the sizes of member variables. C language compiler cannot rearrange the members inside a structure such that the padding will be less. So we have to take care of this fact when we design the structure. So we will see in the demo what are the different combinations we can use, how we can reduce the padding, and we can save memory. So we're going to see this demo. Here I have program which has a structure inside. In this structure we have 4 character variables and 4 integer variables. Everything looks good. Now let's try to calculate the size of the structure. So as I mentioned, size of the structure is the sum of the size of all the elements. So this is 1 byte each, so 4 into 1 equal to 4 plus 4 into 4, 16. So 16 plus 4, total 20 bytes. That is the size of the structure. So let's see what is the output of this size of operator. So this is 14 at the moment, which is 20 in decimal. So our calculation is correct. Now what I'm going to do is I'm going to rearrange the members in the structure. I have rearranged the members like this. So same structure, same elements, only the order is different. Now let's see the size. Now if you look, the size has become 32 instead of 20. So where is the extra bytes coming from? So the extra 12 byte is padding. So now let's look at the memory to understand more about this. So these are the assignments. So our breakpoint is currently here. So all these members are initialized. So the first variable is 1. So we have that 1 here. You can see rest 3 bytes are filled up with padding. So this CCC is padding. They are padding bytes. Why the compiler has added that? So compiler wanted this particular address, which is of an integer, to be on an aligned address. So if this CCC were not there, this integer, so this particular integer would have started here. So this address is not an aligned address. So that is an unaligned address. That will create a problem which we have discussed before. Like that, we have padding up here, here, and here. So total 12 bytes of padding for each character variables, to make sure that these integers in between are on the aligned address. So let's look at the disassembly. So all the D word PTR, if you look at the D word PTR, all this will be aligned. So this is an aligned address. This is an aligned address. So this is an aligned address as well. So all the D word PTR on aligned address. This byte PTR may or may not be on aligned address because it's a byte read or write. Now let's have a look at this scenario in the case of local variable. So again, we have a very simple program up here. All it has is 2 local variables. One is a character and one is an integer. So 4 plus 1, we are expecting 5 bytes of allocation on the stack. Now let's look at the disassembly to understand how much actual allocation has been done. So if you look at here, you can see it is 8 byte sub ESP 8. So the compiler has done 8 byte. In this case also there is a 3 byte padding to make sure that this integer is on an aligned address. So this D word PTR EBP -8, this address is an aligned address. It doesn't matter much in the case of local variable, the padding bytes, but in the case of structure it matters if you're creating a big array of those structures. So you'll be wasting MBs of memory if you don't deal with the things carefully. So make sure that the padding of a structure is the least when you design the structures. Now let's go back to our slides. So we have looked at the memory of the structure variable, looked at the assembly code generated, looked at the size, and we found a difference in different arrangements. We looked at the internals of padding, and we know how to reduce padding. Grouping all the similar elements together is a strategy. Also, we have seen padding in the case of local or stack variable. Now next is the syntax using the arrow operators. So for example, if you have a pointer to a structure, you don't use the dot operator to access the element, but we use the arrow operator, which is given in this particular slide, to access the element. So this is a syntax. Instead of dot operator, we will use this. No big difference. So this is a structure. Instead of dot operator, we are using the arrow operator. Just a syntax. So I'm skipping this demo for your exercise. So pretty much you can look at this program and try to implement it using the arrow operator. Now we are getting into a reasonably difficult topic of finding offset of a member element in a structure. This topic is very important as well because most of the C programming code or the operating system code uses this particular concept both in Linux and Windows kernel or its variants. So we have discussed that structure has different types of elements. More than that, it has padding which is given by the compiler based on some settings, etc. And we cannot correctly predict it all the time. So now the question is how we can get the offset of a member from the beginning of the structure. We have a structure variable. From that variable we can get the address, which is the name of the variable is the address of the beginning. Now what we want is the address of a particular element of that variable. To get that particular element, we need the offset. Why do we need this? We'll see that later. So here is a syntax I'm giving how we can do it. So this is the name of the structure data type, and I have 4 members in it: int a, char b, short c, and int d. So what I want is the offset of this variable or this member from the beginning of the structure. So I need a number. So this is how you get it. So after the execution of this particular line, you will get the offset in this particular variable, offset of d. It is very counterintuitive and it is not in line with the C standards, but everywhere you're gonna see this if you look into the code of an operating system like Windows or Linux. So the offset is, if you can look at it, it is an int star, and this is actually an address. Let's try to have a fake understanding of what is happening. So basically you are assuming some data is there at location 0 is of type myStruct by typecasting 0 to myStruct star. So basically you are typecasting a null pointer to a data type. So the structure variable name, which is also the pointer to the beginning of the structure, is 0. Now what you're doing is asking the compiler what is the address of the member variable d. You are setting the beginning address is 0 and asking the compiler what is the address of D. The address of D will be the offset of D from the beginning of the structure because the beginning of the structure is 0. The complication here is in this particular statement we are clearly dereferencing a null pointer by syntax or by C standard. So this arrow operator is supposed to dereference a null pointer. But actually none of the compiler does this dereferencing, or none of the compiler generate any assembly instruction which actually dereference a null pointer here. We cannot even prove this by looking at the disassembly, as even with all optimization turned off, most of the compiler will generate this particular instruction. Well, this is more of a warning up here, but I believe this is portable as well because everywhere this particular syntax is being used. Now let's try to understand why we need this offset after all. We have gone all the way out to get this offset. Now let's see what is the use of this. In most of the cases we don't need this offset because we have the dot operator and arrow operator. We don't have to index the element manually. We can use the syntax, the variable name, the structure variable name dot the member element, or you can use the arrow operator if it is a pointer. But in some cases you may get addresses which point to the middle of the structure, type which has members A, B, C and D, and you have a pointer or an address pointing to D. In that case you need to know the offset of D from the beginning of the structure so that you can go to the beginning of the structure and index other elements of the structure. This is exactly the technique used in containing record macro in Windows header files. And this particular technique which I have mentioned is used practically everywhere in Windows and Linux kernel. And we will discuss this in more detail when we discuss self-referencing data structures. So now we will see the demo. So we have a structure here, my test struct. So the execution is here and we have 8 up here. So if you look at the disassembly, this is the instruction we have. So there is no dereferencing or anything. Compiler has directly generated this particular instruction. So this is a debug build, so all the optimization is turned off. If you look at here, still all we have is this particular instruction for this particular line of code. You have to familiarize yourself with this particular syntax, although it is complicated. We have another program here which shows the use of offset of an element from the beginning of the structure. So we have a structure data type here which has 5 elements: int A, int B, char CA, int C, and mystruct char link. So in the main I'm initializing a pointer to this particular data type with an allocation. So I'm doing an malloc with size of mystruct. So I'm initializing a couple of variables after that. So A, B, C and CA I'm initializing. I'm not even initializing the link because I don't care what is the value inside the link. All I care is the address of that link. So what I'm doing is I'm passing the address of link, so the address of one member of this particular structure. So I'm passing that into a function. This function takes void pointer. So all it needs is a pointer of any type. Inside the display, what I'm doing is I'm calculating the offset of link from the beginning of the structure using the technique we have discussed. So I'm typecasting it to int here because, as we discussed, this is an address. So now I am assigning this ptr to a character pointer. So I'm typecasting it here. So now to go into the beginning of the structure, what I'm doing is I'm subtracting the offset from this pointer. So this pointer is assumed to be point to link. So I'm subtracting the offset of link such that I will reach at the beginning address. So these three lines are the most important line which we have to understand here. So I'm getting the offset here. I'm initializing a character pointer with the address of link. So what I want is the address of beginning of the structure. So for that I'm subtracting the offset from the address of link. After that, all I'm doing is trying to access the elements. So we should get the same elements here. The point is I'm not passing this particular value to this function, but I'm passing the address of a member of the structure, and I'm finding the offset of that member, and I'm finding the initial address or the beginning address of the structure. So I have a breakpoint here. So if I start executing, so with no surprise we are getting a equal to 10, b equal to 20, c equal to 100 and c equal to 50. So those are the values we have assigned here. Some general facts about structures to conclude. Structures can contain structures, union or array or any other data type. We treat a once defined structure like another data type, like integer or character. So structure is nothing but a custom data type. We can create array of structures, get address of it. We can do anything like that, any of the combination of those kind of operations. Pass array of structures to another function, return, etc. So we'll see an array of structure and a structure inside a structure. So we have a structure here which has two integers, and there is one structure which is inside this particular outer structure. So again it has same name, just to show that it is inner and there is no conflict. So this inner is of type this inside this. So these are the members of this inner. So the access is done like this. So I have declared an array of outers, and this is accessed like this as normal. So here is the array index. This is accessed like this, inner dot a and inner dot b. So any this kind of combination is allowed, but I recommend in production code you should make things as simple as possible, because you will have so many other complications to deal with. So now let's go back to our slides. So we have seen the array of structures, we have seen structure inside a structure, we can have union or anything like that, and that's it. Thank you very much.